Hey guys, Mr. Betts here. In our last topic, we talked about how to find general solutions to differential equations using a process called separation of variables. Now we're going to take that a step further and use an initial condition, which is a point that we know the solution is going to pass through to find what's called a particular solution. So one solution, one function that is a solution to a differential equation. We have looked at particular solutions before. So if we have a differential equation like this one, and not only do we have a differential equation, but we also know a point that differential equation, the solution to that differential equation is going to go through, we can find a general solution, which involves that constant of integration, but then we can use that initial condition to solve for the constant of integration and get what's called a particular solution. So this function right here is the one function that satisfies this differential equation and goes through this point. So that is called a particular solution. So just some general terminology here that you need to be familiar with. An equation that has a derivative in it is a differential equation. A point that the solution to a differential equation is going to go through is called an initial condition. The general solution has the plus c, or that constant of integration, involved in the solution in some way. And then the particular solution is what we get when we solve for the constant of integration and plug that back into the general solution. So just a quick refresher, I'm going to go through this really fast. Finding a general solution using separation of variables, we separate variables. We take the antiderivative of both sides. When we take that antiderivative, we introduce that constant of integration, and then we solve for y. So we get y by itself, so we have a function that is a solution, and with the constant of integration in there, that's called the general solution. What we're going to do is we're going to take a differential equation like we had before and introduce this initial condition so that we can find a particular solution. So I'm going to go through that process with this particular example here. So we're going to separate variables by multiplying by cosine of y and multiplying by dx. Then we're going to take the antiderivative of both sides. So we get, sine of y is equal to x squared plus x plus c. And then solving for y by using the arc sign, we're going to get y equals arc sine of x squared plus x plus c. So that right there is what's called the general solution. Now we're going to go beyond this, and we're going to use this point right here. So this right here is the x value, this right here is the y value. So we're going to plug 0 in for y, plug 1 in for x, and knowing the properties of sine and the inverse of sine, or arc sine, we know that the arc sine of 0 is 0. So we should be getting a value for c that makes this inside part here 0, which is going to be c equals -2. And so plugging that back in to the general solution, we're going to get y equals arc sine of x squared plus x minus 2. And this right here is our particular solution. Now we're going to go beyond just finding the particular solution, and we're also going to look at domains of our solution. So there are certain x values where this is a valid solution to the differential equation, and there are some x values where it is not. So we will talk a little bit more about that later, but the idea here is we're going to take a general solution and an initial condition, plug it into the general solution, and get a value for our constant of integration. So the general process of finding a particular solution is going to be finding the general solution, then using the initial condition to solve for that constant of integration, and then we do want to determine the domain of the solution. So looking at step 2, one thing I do want to point out is that we can solve for the constant of integration before we solve for y if we want. So just looking back at this example right here, when we had this equation right here, it might have been easier to solve for c at that point by plugging in 1 for x and 0 for y, and then solving for y, and you can do that also. So it doesn't matter if we get the general solution as a function first, or if we solve for c and then solve for y. The other thing I want to point out about the domain is that the domain of the particular solution should only contain a continuous branch of the solution. So what that means is if we have a function, say like the tangent function. So the tangent function, remember, has vertical asymptotes at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on. If we have a particular solution that is the tangent function that goes through an initial condition between negative pi over 2 and pi over 2, then we're going to exclude everything that's not in the continuous part of that from our solution, because we don't know when we jump over a discontinuity whether we're going to have the same constant of integration or it might change. So it's really important that we only include in our domain a continuous branch of the solution function. So I want to look at this example again, and I'm going to go through it kind of quickly, but a slightly different way. So I'm going to use a definite integral to solve this. So this is an alternative method for solving where we don't have to use a constant of integration because we are using definite integrals. Remember, evaluating definite integrals, we don't use that plus c. So here's how that process is going to work. We're going to start the same way we did before. We're going to separate variables. So we've got cosine of y is equal to the quantity 2x plus 1 times dx. Now, here's where the change is going to be made. When we take the antiderivative, we're actually going to take a definite integral, and we're going to use for our lower limits these values right here. So again, remember, this is x and this is y. So my lower limit on my y integral is going to be 0, and my lower limit on my x integral is going to be x. Now my upper limits, I want to be the variables x and y. However, with definite integrals, I can't, I made a mistake here. Need a dy in here. I can't use the same variable as I have as part of my differential or integrand. So I'm going to use a capital Y and a capital X. This should be a 1 here. And I'm going to evaluate these. In the end, this capital Y and this capital X, I'm going to change back into lowercase y and lowercase x. And we are going to end up with the same solution. So to evaluate this definite integral here, we're going to take the antiderivative of cosine, which is sine. It is the sine of y, and we're evaluating that from 0 to y, capital Y. On the other side, we're going to take the antiderivative and get x squared plus x, and that is being evaluated from 1 to big X. So evaluating that, we get sine of big Y minus sine of 0 equals big X squared plus big X minus 1 squared plus 1. Remember, sine of 0 is 0. So this is 0 here. So we get sine of big Y is equal to big X squared plus big X minus 2. And this might be looking familiar to you. Last thing I'm going to do is solve for big Y, but I'm also going to change the big Y and the big X to little y and little x. So we're going to take the arc sine on both sides. So we get Y equals arc sine of x squared plus x minus 2, and that is our particular solution that we got using the other method as well. This is just an alternative method. It's not one that I would necessarily recommend, but it does allow us to get all of the work in one workflow rather than having to do a little bit of side work when we're solving for that constant of integration. So it is kind of a personal preference thing. In general, I will solve these problems by getting a general solution using antiderivatives, not definite integrals, and then solving for the constant of integration and then plugging it back in. I also want to point out that the arcsine function does have a domain restriction from negative pi over 2 to pi over 2, and it only gives us y values that range between +1 and -1. So if we are looking at restricting the domain here, this expression on the inside is going to have to be between -pi/2, between -1 and 1, so that the y values we're getting are between -pi/2 and pi/2. So I encourage you to watch the example videos to see some more examples of solving differential equations with initial conditions to get particular solutions.